Hi, in this video I will give more details about the derivation of the elastic string displacement equation that is presented in this reference, A First Step Toward Variational Methods in Engineering by Francisco Periago. The original derivation is on page 3. You can see the situation here. You have a elastic string which, if there is no force on it, will be at rest from 0 to L. So the 0 position is here, horizontal, and u of x is the displacement from the horizontal position. All right? So let's go and see what we can do with this equation. All right, so first what we do is we parameterize the string by s according to its original position. The string's displacement is given by w of s, u of s, where x and y give the horizontal and vertical position. Horizontal and vertical direction. Note that an undisplaced string will have ws equals s and u of s equals 0. All right, so let me try to explain what I'm saying there. So this is derivation of string equation. All right, so let's look at this. All right, so the undisplaced string has this position from 0 to L. Right? Okay. And for an undisplaced string, this distance would be s. Okay. Now when the string is displaced, this point at s experiences both a vertical and a horizontal displacement. So the vertical displacement is this way. That would be u of s. And the horizontal displacement might be to the left or to the right. So that would be w of s here. Okay. So this point, when displaced, goes down to this new point here. And all points in the string similarly. So the string will go like this. Every original point on the string will move to another point on the displaced string, something like this. I don't know where it will move, but we'll just say that the string points are being displaced and the new positions will be at these corresponding red points. Okay. All right. So let's see what happens and what forces are involved in maintaining the new shape of the string. Remember, the reason why this string has a new shape is there is an external force pushing down on the string. The force may vary along the length, so that force is a function of s. So let f of s be the vertical force per unit area applied to the string. Really, this should be per unit length, okay, because the string has a length, not an area. Okay. We suppose that there's also a vertical restoring force density that is proportional to the displacement u with constant proportionality minus lambda of s. Because the string is elastic, it resists being moved. So there is a responding force at each one of these points, responding force that wants to move the string back towards the vertical position. So at each point here, you're going to have a restoring force. So the restoring force here would be lambda, and that's lambda of s times u of s, where again, s is going to be my independent variable. So note, in this setup, we're going to have dds of u is equal to u prime. All derivatives are with respect to s. S is the independent variable. And s is the position of the point along the string in the undisplaced state. So I hope that's clear. As I said, this point, undisplaced point, will move down to here and will have a different position. But that new position can still be parametrized by s. So that's what we have now. So the total external force is a function of s, and it depends both on the applied force, which is little f of s, and the restoring force, which is minus lambda of s, u of s. And this is in the vertical direction, so I write it as a two-dimensional vector. There's no component along the x direction, and then there's a component along the y direction that's given by f of s minus lambda of s times u of s. So, to derive the equation for displacement of the string, we will use Newton's third law. And for any object that is not accelerating, All forces exerted at all points within the object must sum to 0. You may know Newton's third law as force equals mass times acceleration. If acceleration equals 0, that means force equals 0. So that's what we have here. So the force along the string is called a tension, denoted by T of S. So let's look at this small point here. Let's just look at this individual point here. Okay. Now this point is at location U of S, W of S. Okay. So I'll make the large picture down here. So the point is red, so we'll put it in red. And the string is also moving. Now the string is bending like this. The location here is W of S and U of S. Now the tension force is along the string because the string is pulling. A pulling string can only exert force along the string. So the tension force here is in this direction. Now let me call this S0, and here I'll do another one that's S1 over here. So this is W of S1, U of S1. Okay, 2 points along the string. Remember when we did the heat equation, we also looked at a small section of the rod. Now we're going to look at a small section of the string. So this here is going to be my tension at S0 as a function of S0. And that's a vector because the tension is parallel to the direction of the string. Here I've got another tension, and this is going to be tension at S1. So these two different tensions will exert varying forces, and the varying forces here will have to balance against the external force. So the sum of tensions plus external force is equal to 0. So let's see how we can express the net tension force. Okay, that's the key to this derivation. What is the net tension force? So what does it say here? The expression for the tension force is given by this expression here. So let me copy that and we'll put it down here. All right. So I see now I need to change my notation a little bit. Here I shouldn't call this T, I should call it Ft, because Ft is the vector that expresses the tension. So let me correct that. So this is Ft, vector force of tension, and this is Ft of S1. And they're in different directions. Now the force of tension is equal to some constant times this quantity. Now what is this quantity? This is a 2D vector. And this is a length. So in fact, what this quantity is, this is a unit vector in the direction of the string. And you can see that unit vector is in different direction here and here, okay, because the string is curving. All right. So let me emphasize that this point is WS, this is S0, S0, this is S1, S1. Now Hooke's law states that the tension of a string is proportional to the magnitude of the stretching of the string. The stretching of the string is the derivative of the displacement. That's how much the string is being distorted along the length of the string. And the constant of proportionality is K of S. So we have an expression for T of S. We can put that in there. Now notice we have this quantity here is the same as this quantity here. So that's very useful. Let me copy that. So we can replace this expression for T of S down here. We can express this expression for T of S into here. And that will give us a simplified expression for the force of tension. Okay. So the difference between the two forces of tension at S1 and at S0 plus the external force is equal to 0. Exercise. Use the y component of this equation together with equations 1 through 3 to derive the equation for string position. And what you'll get is this equation here. Notice this comes from the external force. This is going to come from the restoring force of the string. And this is going to come from the tension. Now the derivation is similar to the derivation of the heat equation. We are going to get an integral equation, and the integrand will be 0 on every interval from S0 to S1. Okay. So you will derive the string equation first in the form the integral from S0 to S1 of a term arising from the net tension The net tension is the tension on both sides of the small interval. You'll have to add those two tension forces together, and you can notice that they oppose each other. You see, this is an opposing force, but they do not quite cancel. So we're going to have a difference there. Is equal to the integral from S0 to S1 of the applied force density, and then plus the restoring force. I should make clear up here that this F is the vertical force per length, so that's applied force density. So similarly, the lambda times u is a restoring force density. So try to put those things together and make a derivation of the string equation. This write-up is in your homework sheet, which you can obtain from Canvas. It's on page 3. It's in set 2. All right, so hope that you can make some progress there.